Okay, buzzer, very close. What drives the buzzer? Sorry? What drives the buzzer? It's a circuit that you guys did quite fast, right? Anyone? The group A students? There's a circuit in your lab 6 that actually behaves like a digital to analog converter. Sorry? Okay, it's actually the PWM, right? So you hear the buzzer, right? The buzzer produces a sound which is analog in nature, right? Because we cannot hear digital bits, but we can hear an analog signal. The PWM is a digital circuit, right? When it drives your buzzer, it performs an intrinsic digital to analog conversion. So indirectly, a PWM circuit is a D to A converter. Okay. So for the actual D to A converters is more elaborate, which is not covered in this module. Maybe in the future we will. Okay. So I will spend some time to talk about the A to D converters. Okay, and then more for the lab or interfacing with microcontrollers for the ADC, and then a briefing on lab 7. I hope most of you have started your lab 7 in your week 7 break, right? I know some of you completed, but I hope the rest also started. At least load in some code, okay? Okay, so here's the overall diagram. So our real world, okay, our real world, the world that you live in, that you are sitting in right now, are all analog quantities. Okay, sound. When you open your eyes, you see light. These are all analog quantities. And what else? Sound. When you breathe in the air, the flow is actually also analog. There's no digitization, right? And then when you drive a motorcycle, like some of you do, when you measure the speed, it's also analog, right? Or when you step on the accelerator, it's also analog. But for most of the modern world, we also need to digitize them. We need to digitize our analog world, right? And that's where blocks like A to D conversion comes in. So there is a boundary between the real world, the world that you and I live in. Sorry, spelling mistake. And the virtual world. Okay, some people call it virtual. People call it digital, right? So the window to the real world and the digital world is the A to D converter for getting real world quantities into the virtual world. This is called A to D conversion, or some people call it ADC, or some people call it analog to digital converter, right? And then the D to A converters will convert your virtual world back to the real world. That's called the D to A converter. Okay. So we may talk about digital economy, what our government has been talking about, digital economy. They are just talking about this. Okay. So as SEM students, all of you here are actually important people because you will know how to interface the real world with the digital economy or the digital world. Okay, that's what makes STEM students so special. And computer scientists, they only work in this world, right? So take note in mind, right? So indirectly, you're learning something very valuable. Okay. Actually, this is what I talked about just now. So A to D is the window into, right? This is the input. The real world or the analog world into the digital domain. And then this is the door that goes out, right? Goes out to the real world again. Anybody watched this movie Matrix before? Matrix. Anyone? No, huh? Okay. Maybe yeah. Maybe it shows that I'm too old already. Matrix. If you watch this movie Matrix, this special agent will pick up a phone, and then instantly he's taken back to the real world because his actual world is actually in the digital domain. This is like the Matrix, right? But he actually is a sleeping human in the real world, but all his thoughts are all digitized. So it's a bit when I see this diagram, it's a bit relevant. I'm not sure what is the latest movie that actually has this translation, but maybe closer to our daily life is the digital economy. Okay. All right. Now so interfacing with A to D converters or D to A converters is actually not that easy, as maybe some of you have already experienced. It's not that easy. These are creatures, I call them creatures. They are not easy to deal with. And also, they are also not easy to design. That's why microcontrollers with MCUs or with ADCs or D2A converters are usually more expensive. These blocks are actually expensive to design. Okay. Before I go to here, so I will do a whiteboard. Just okay. So how do we digitize analog signals? Okay. So this is something that is not covered in the lecture. Okay. So just pay attention. So in our analog world, suppose this is the XY graph. So we have a analog quantity. Okay, and we assume most of our real world quantities, they are all linear. Okay, line graph, they are linear, right? And let's say we have a maximum signal. Let's say a voltage V max, and we have a minimum voltage V min. So this signal itself in the real world is a continuous signal. Continuous. Okay, it's a continuous signal. It's a linear signal. So how do we digitize it? Okay, how do we digitize it? So in the simplest forms, let's say we are given an ideal 3-bit A to D converter. Okay, 3-bit A to D converter. So for 3 bits, how many discrete steps can we obtain? Someone from group A? If it's a 3-bit digital domain, how many discrete values can we have? How many? 2 to the power of 3. What do we get? 8, right? We can have 8 discrete steps. Okay. So we have now in this case, can we then because we need to discretize, right? We need to discretize. Let me write it here. For A to D converters, we need to convert continuous signal to discrete levels. Okay. So I just take 3 bits as example, right? So what do? We will chop up the signal range, okay, into 8 distinct steps. So 1, 2, 3, 4, 5, 6, 7, 8, right? So, and then we can map it to a digital signal step. So suppose this is 0, 0, 0. This will be 0, 0, 1 for 3 bits, right? So this will be 0, 1, 0, 0, 1, 1. Okay, pardon me for my drawing. So and so forth, right? This concept is actually not covered in the lecture notes, but I will just draw it here, and so on. So you actually segmented or discretized your analog range into 8 different steps. So as I continue, okay, so let's say 1, 1, 1 here to give you the maximum. So there will be 8 steps. this is how a D to A converter will see an analog signal. Suppose if your analog signal is here, the D to A converter will directly convert this voltage to a discrete level of 0, 1, 0. Okay, so if you do it mathematically, right, this analog signal is like say 1/8 of the Vmax. Suppose Vmin now is 0 volts. Okay, so this will be 2/8, and so on, 3/8. This is how the A to D converter will discrete signal. Okay, a signal that is beyond the halfway point, it will round up to the next highest digital level. It's like rounding up and down. Maybe I go through this again. Give me a moment before I show this one. Where's the whiteboard? Just a moment. Okay, let me repeat what I mentioned. Okay, this one is very important so that you can. It's not just for this course. It's more for general. Okay. So I go through again. So we have an analog signal. Say this is Vmin. Okay, analog signal. Let's say 0 volts, and you have a Vmax. So if you have an analog signal that increases linearly, okay, this will be corresponding to this. So the A to D converter will define a few ranges, right? So 3. How many do we have? 8. Okay. So in this case, if the analog signal is 1/8 of the Vmax, it will register as 0, 0, 1, and so on. Okay, so this will be 0, 1, 0. So this is just for 3-bit A to D converter. And finally here, this will be 7/8. Vmax will be 8/8, right? This will be digital 7. So between this, any signal that falls between this range will be discretized or quantized. Okay, the actual word is called quantized. It will be quantized into a corresponding digital signal. Any analog signal that comes in between here, okay, or here. So in the next range, for example, so if it's 0, 1, 1, if your analog signal is here, say this is 2, 3. If it's 4/8, you'll be quantized into this digital level. Okay, so there's a mapping. The A to D converter will do the mapping for you automatically. All right. Now imagine now instead of 3 bits, right? 3 bits, we have more bits, right? The same concept happens, right? So now let's say we have 6 bits. You have more quantization level. You start to see that you can actually resolve small. Okay. So as you have more and more bits, say instead of 6 bits now, you have 12 bits. You can quantize even more. It's very hard to draw, right? Okay. Not 6 bits, sorry. This is just now was 3 bits. So 4 bits, 5 bits. So as the bit, if the number of bits increases, you can actually quantize smaller and smaller voltage range. Right? This is called resolution. So a higher ADC with a longer bit width will have a higher resolution. This is what it means, right? So for a 3-bit ADC, the resolution level is 2 to the power of 1 over 2 to the power of 3. Your resolution level is only 1 over 8. Anything that's in between will be either averaged out or will be rounded up or rounded down. So this is how the A to D converter will work. Okay, so take note of that. So in this case, suppose you have a sine wave. Let's say a sine wave that is analog in nature, and you have a 4-bit ADC. Okay, the ADC will only discretize in the blue line. So this is how the ADC will see in the blue line, right? So in a way, the A to D converter will only see these sine waves as steps. So that's for 4-bit resolution, right? So it's a bit rough, right? It's a bit coarse. Now imagine if you have more bits, then these steps become smaller. So small that our eyes cannot even see. So I will say so fine that you cannot even see. Can anyone make a guess? What is the resolution of our eyes to resolve these steps? What is the best resolution that our eyes have? Make a guess. How many bits? So this is only 4 bits. Our eyes can resolve how many? Our eyes cannot resolve 2 bits. If it's 2 bits, we become a binary machine, right? Our eyes can resolve at best in the reading distance 8 bits only. 8 bits only. So when I say 8 bits, right, means the resolution level for this kind of steps is 256. Because 256 is 2 to the power of 8. That's why in the next trimester, when you look at the oscilloscope specification, the oscilloscope is only 8-bit resolution. Okay, it's really expensive already. So if you have more bits, right, it's quite useless, but become more expensive. Okay, our eyes can resolve a fine resolution of only up to 8 bits. Okay. So I actually cover this very quickly. So this is just a reiteration of what I mentioned. So suppose you have a 2-bit ADC and you try to resolve an analog signal. The ADC will come up. If you just plot the output of ADC when doing sampling, you'll come out with just a blue line. So it looks like a bit of sine wave, but it's actually a bit coarse, right? But then if you increase the resolution from 2-bit to 3-bit, it becomes less coarse. Okay? The quantization level has decreased. And then you go to 4-bit, it looks more and more like sine wave. So for certain applications, it's quite useful. It's just good. It's good enough really. But for audio applications, even 8-bit is not enough. Make a guess. How good are our ears in resolving? How many bits are our ears can resolve for audio signal? Make a guess. Our eyes 8 bits, right? How about sound? How good are our ears in resolving sound? Make a guess. Anyone from group B? It's 24 bits. Our ears can resolve 24 bits. Means our ears, in a way, is actually more sensitive than our eyes. Okay, so it's actually more important to listen than to read. Okay. So in certain cases, right, you realize that why the indicators usually have sound. It's because of our ears can listen very well, 24-bit resolution. So even a little bit of sound we can hear, eyes can't, right? So just take note of that. So just a mathematical calculation. So what is the resolution? What is the quantization error? So in the ADC terminology, we call this a 1 LSB. So from one step to the next is called LSB. Okay, LSB means least significant bit. Okay, so what is the least significant bit? How do we calculate, right? So for 3-bit, let's say the 3-bit terminology, 1 LSB resolution is defined by taking your maximum signal, subtract your minimum reference signal, and then you divide by the bit resolution. So suppose your maximum supply voltage, for example, is 3 volts, and then your minimum so-called reference signal is 0 volts, and then you have a 12-bit ADC like your lab, right? Okay, you can quickly take a calculator and calculate. I think it should be less than 1 millivolts. In fact, less than that, right? 2 to the power of 12 is 4096. Okay, so if you do digital circuits long enough, you'll realize these are numbers that you can read offhand. Okay, so this is like close to 200 microvolts resolution, enough to receive radio already. Okay, so this is the how small your resolution can be, right? So this is one of the parameters that if you go shopping for microcontrollers, okay, this is one of the first parameters you look for. Okay, so not just for the exam, not just for the course, I'm actually sharing with you if you notice things that's outside of this course, but may be useful for you. Okay. Now, I forgot to mention. So for these two voltages, right, some data sheets come in confusing ways. Okay, some data sheet only give you this, and they don't give you this. So if they don't give you the minimum signal, assume 0 volts. And if they give you this, is usually the supply voltage, 3 volts. Sometimes if you use special microcontrollers, they will generate this reference voltage for you internally. It can range from 1.8 volts to even up to 10 volts. Okay. So ADCs, they are not perfect creatures. They are not perfect. So they have some errors, and like the gain error and offset error. This one you can read up in your own free time. Okay. When you do high precision audio, you need to take care of this. But if you do your lab 7, you don't have to worry about this. Okay. What else? Okay. So resolution is the first thing that you need to look for. So for our lab 7 microcontroller is 12 bits. Some systems give you 10 bits only. Okay. I'll forget to tell you. So when you shop for microcontrollers, they can tell you, okay, I have a 12-bit ADC. It does not mean the resolution is 4096. Okay. Sometimes, depend on the manufacturer, they actually, some of the bits that inside the range have errors. So in a way, the 12-bit ADC may actually behave like a 11.5 bit or 10.5 bit ADC. Means the resolution is actually less. So depend on how good is their marketing department. They may actually hide this fact from you. So please take note. So when you're doing really high precision work, right, you have to take note of this. I know some of you here do audio, so I like to share this with you, right? So the 12-bit ADC is not in some of the MCUs that you may come across, right? So you have to take note that they may not resolve exactly 4096. Their resolution level may be just this much only. So take note of that. Okay. But for some companies that I encounter, what they do is that they know this is imperfect. They know that ADC is imperfect. So what they do is they will design internally, they won't tell you, a 14-bit ADC. But then they will market this as 12-bit. It's a very honest company. Okay, there are some companies that does that. Okay. So now the reverse, right? This formula, maybe I should just erase this. So from this formula, you can also back calculate the range or the voltage level. Okay. So suppose you you have an ADC, right, in your lab 7, you read a digital value. Okay, so for example, let's not do so complicated. Let's do a 3-bit ADC. So a 3-bit ADC, your maximum range is 8, and then you read a digital value 011 from an A to D converter. So what does it mean in the actual analog voltage, right? So you can back calculate. So if your Vmax is 3 volts and your Vmin is 0 volts, and when your ADC gives you this voltage here, you can actually back calculate what voltage is it actually reading. This one quite useful, okay? Because you can play with audio, you can play with sound. How much sound are you receiving? How much voltage are you receiving? You can actually use this formula to back calculate. It's all derived also from the. I won't ask you to derive. It's actually derived from this this formula here. Okay, so just take note of this. So of course, if you have higher bit resolution, you need a calculator for that. Okay, we actually use this to calibrate ADCs in the industry. The same formula. Okay, so for ADC, the first and foremost parameter is the resolution, number of bits. The higher number of bits, the higher the resolution. The world record for ADC resolution is 32 bits, but very expensive. Okay, world record. The ones that you actually listen to in your CD players or your iPod is 24 bits. Okay, they use a very special ADC that can actually reach that kind of level. Okay. The next parameter when you go shopping for ADC is sampling rate. So A to D converters, they always do sampling. What do I mean by sampling? So you have an analog signal, right? The A to D converter will repeatedly sample a signal. So A to D converters, they usually have a clock. They have a clock and they will keep sampling. Okay, so they will always hear this word sampling rate. Okay, sampling rate. So for I think for the lab is 1 megahertz clock. So the sampling rate is 1 mega samples per second. You always see this word MSPS. Okay, mega samples per second means in 1 second. In 1 second, your A to D converters samples is input at 1 million times. Okay, mega samples per second. Some cases may not be that fast. May not need that fast. Okay, so some of the general microcontrollers or ADCs that you can buy off the shelf, you just buy what you need. Okay, you just buy what you need. But how do you know how much what is the highest sample rate that you need to buy? Okay, it's based on this term is actually not covered in the lecture, but good to know. Nyquist. Some of you may already study Nyquist sample rate theory or Nyquist theorem. It means you will need to buy an A to D converter that is at least that has a sample rate that's at least 2 times your highest frequency of interest. What do I mean? Okay, just a moment. Suppose you have a sine wave, right? Let's say this sine wave, we don't worry about the frequency first. Suppose your ADC, right, only samples twice as fast, right? This, or maybe this is sorry, what's this? The ADC only samples here and here. Suppose this is 1 microsecond. So the frequency of this sine wave is 1 megahertz. But then the A to D converter also sample at 1 mega samples per second. So it samples here and sample here. What happens? In the way the A to D converter only see a continuous 0. Why? Because it only samples here and here. Okay. So usually, if you choose a microcontroller, Okay, so people in the street will tell you, oh, your sample rate is going to be 2 times faster. Actually, the truth is it has to be 4 times. What do I mean? So in this case, if I can redraw the whole thing here again, and I sample my sine wave 4 times. Say I sample here, here, in fact 5 times, here, and then repeat, right? I can actually reproduce the sine wave in a way not so nice, but I can reproduce it. So this is the limit, but the information is there. It's actually positive or negative. Of course, if you really want to reproduce a sine wave, you need to sample faster to get a really nice sine wave. So nice that your eyes cannot even resolve 8-bit resolution. Okay, so your sample rate got to be usually much higher. So for a 1 mega samples per second A to D converter, your highest signal of interest in theory, Nyquist, is 500 kilo samples, 500 kilohertz. But actually, you should just confine to 250 kilohertz or even less, right? It's because of sampling. The ADC takes time to sample, okay? So let's go for the next one. Okay, so it's called sampling rate. So we have resolution and sample rate. Okay, so these are 2 different terms. They are actually 2 different quantities. So sample rate means how fast your ADC sample. Okay, resolution is how fine your signal gets quantized. Okay. In most cases, these 2 terms, they are not related, but there is a physical limit. Okay. So you can buy an ADC with a very high sampling rate, but usually you will realize that the ADC resolution is very low. Okay, there's a physical limit to it. Or you can have a high resolution A to D converter, but the sample rate is very slow. Okay. So what do I mean? So this one is more for your general knowledge. You don't need to know. This one is created by my friend in Stanford. Yeah, I visited him last February, so he told me this. So he actually came out with a line. Yeah, these are all the different ADCs that was published by his friends. So there is actually a physical limit, how fast you can sample versus the resolution. Okay, so just forget about this term first. It's actually resolution. Okay, it's called SNDR. So a bigger the number, the more resolution you have, right? So you realize that I can have a very high resolution ADC, but then my sample rate is low. There's a trade-off. Okay, there's a trade-off. Then you can have a very fast A to D converter. This is more for oscilloscopes. The resolution is really bad. It's only 20 dB. It means it's like close to 3 bits. Okay, these are all the compilation that he did over the years, since 1997 to in fact this year. All the world top A to D converter designs, he compiled all of them. Okay, so if you want to know more about how he do it, you can go to his website, and he even give a very short video on what he's actually a world expert in ADC. So he actually explains to you in an even simpler form. Okay, if you're interested to know. Okay, so how in the A to D converter circuit, how does it look like? Okay, this one is designed by me and my colleague when we were in NUS. So I just want to share with you. Actually, A to D converters are just a series of switches. Remember, you touch the switch in lab number 1, right? You press a switch and the LED lights out, right? Same concept, but these switches are implemented by transistors. And then we use capacitors. Capacitors you will see in EC210. Then we have comparators. You should see also in EC210 Then we have oscillators. We actually create the oscillator on the chip. And then logic. Does it ring a bell to all of you? Lab 3. Your logic circuits. So it's a logic circuit to do the discretization, right? You want to discretize your voltage levels. There's a logic circuit that actually is running in the background, right? So for this ADC, we receive an input, and then we generate a 10-bit output. If you're interested, you can read about the paper here. I think the school actually subscribes to it. Okay, and this one is actually used to record signals from the brain and from our nerves. We actually use that. So you may wonder why I actually talk about ADCs for so long, because I actually have a real interest in it. Okay, one of my research is actually on ADC, right? Oh, by the way, this ADC circuit is very small. So if you open our MCU, it's also exactly that small. It measures only 360 microns by 380 microns on the chip. Okay, so if you want to know more about the ADC design, you can come to me. We can discuss offline. If not, we will proceed to the actual lecture. The ones that I share with you is more for general information. Okay, it's for you one day if you ask your boss asks you to go shopping for ADC or MCU, the 2 parameters you need to know: resolution, sample rate. And if your boss one day asks you, can I find an ADC 24-bit sample at 1 gigasamples per second? Cannot. Why? Because Dr. Ng say cannot. And his friend in Stanford say cannot. Show him the graph. Okay? Then your boss said he still wants. Maybe you will have to get this guy in Stanford to design for you, but he will charge you very high, okay? The world fastest A to D converters right now, I think it's around 10 gigasamples per second, made by HP Keysight. That's actually used in oscilloscopes. Okay, let's go back to the practical world. Okay, practical world. Okay, so where were we? Okay, so for the MCU, we actually have a 12-bit A to D converter. We actually have an A to D converter on the chip, right? And this is the specification. So it's a long name: successive approximation analog to digital converter, right? What does it mean? Okay, I won't go through the detail, but I will say, remember you were asked to convert a decimal number to a digital number, to a binary number. Remember, what do? You do divide, right? A few divide, right? The successive approximation A to D converter is actually doing that. It's actually doing that. It's doing division in voltage in the circuit itself. So some people like to use this term, successive approximation. Sometimes you see data sheet 12-bit. Okay, they have another term. It's the same thing. Don't get misled by them. SAR ADC. SAR is not the weapon you use in SEM. Okay. It's not SAR-21. So SAR ADC, successive approximation register ADC. Sometimes you see this term. It's a SAR ADC. Okay. So there are generally 3 classes of ADCs that you can see in MCU. The SAR ADC is the most common one. Okay. So if you use when you speak to engineers in the industry, SAR ADC, they may think that you come from NTU or NUS. Okay, so it's something that just keep in mind. Okay. Sometimes you may see another kind of ADC called pipeline. Pipeline ADC. Some MCUs actually have that. This is very fast. This is faster. So SAR ADC, if it's 12-bit, right? You can see in the diagram here. Usually SAR ADC take 12 clock cycles to complete one conversion. The pipeline ADC take 1 clock cycle. So it's very fast. But it has a latency. This one I won't go through. But for your general knowledge, it's either you you will see SAR ADC or pipeline. If you see another kind of ADC called flash, you are actually running a Ferrari, right? Because flash is even faster than 1 clock. But flash is actually very expensive, very power hungry. So they don't usually put this in your MCU. Usually you see these two. Okay. So for SAR ADC is more general purpose, more generic. Okay. So what does the SAR ADC in a way, when you see this clock diagram here, right? What does it do? Okay. So usually you have an input signal to tell the SAR ADC, okay, start convert. Then the SAR ADC will go through the same thought in your head when you do your decimal to binary conversion, divide, because it's 12 bits, you divide at least 12 times, right? So you see the clock cycles coming in, you do at least 12 times. Of course, they will still have some extra clock cycles to do some makeup, right? Makeup. They will do some housekeeping. So usually more than 12 cycles, usually 14 to 15 cycles. Then after they finish conversion, they will tell you, okay, I'm done. So there will be a start convert and done signal, and then the ADC will give you 12 bits of your converted output. So there will be usually a delay. So take note of that. You actually when you ask the ADC to convert for a SAR ADC, it won't give you the result straight away. You have a delay. But this delay, because the SAR ADC works so fast, is usually in human terms not noticeable. But if you do timing critical applications, especially for life saving applications, you need to take care of this, right? For audio, maybe not. Maybe audio will be some distortion if it's too slow. That's all, right? Just take note, okay? So I'll go through these points later. So it's a 12-bit conversion. Sample rate, this is 200 kilohertz. So it's a very confusing term. So some people say put hertz, some people say samples per second. The actual correct term is 200 kilo samples per second. Depending on which country you come from. Okay, so for every 1 second, it do 200,000 conversions. This is what it means. Okay, at a resolution of 12 bit. All right. So, and for some of you may encounter, sir, I only see one ADC in the MCU. Why you can accept eight inputs? So there's the feature in the MCU. It is called multiplexing. So you have 8 inputs, right? There's actually a multiplexer to your ADC. So it actually multiplex. So at any one time, you can only read one channel, and then it will sequence through the remaining 7 channels and then repeat again. So that's what it does. So your ADC, in fact, if you do the sequencing through, right, even though the ADC is 200 kilo samples per second, the effective sample rate, right? So I call it F sample, is 200 kilo samples per second divided by 8. Take note of that. If you want to read all your 8 channels simultaneously, your effective sample rate drops by 8 times. Okay? Unless you have 8 ADCs in a chip, which is very, very expensive. Okay? Okay, so this is what it does. And there's a measurement range. Okay, just a moment. So remember I talked about the VREF positive, the maximum, and the VREF negative, which is the minimum. So in the chip is 3 volts for MCU. So you notice there's only VREF P. So inherently this value is 0 volts. So your ADC conversion range is 0 to 3 volts. What's the resolution? You can calculate 3 minus 0 divided by 2 to the power n, which is in this case 4096. All right. So of course, like I mentioned, if you want to do high resolution acquisition for audio or for something special, don't take this number wholesale. It may actually be less because the ADCs may have errors. Okay, don't use out the full range. You may actually get errors, and it can be quite fatal for certain cases. especially if you do servo motor control. If your ADC resolution is not what it is promised, you may get oscillation. Then your servo motor may run out of control. Just take note of that. Okay, but at least for this course, you may not see it. But in your future adventures as an engineer, you may actually see it. Okay. Okay. So just now I mentioned about the cycling of 8 inputs, right? And then you cycle back by multiplexing, right? It's actually doing burst. We call it the burst conversion mode. Okay. So this is basically the spec. Okay, so I walked through the spec with you. So I hope you you can understand this. This is more for you to go shopping when next time. Okay. Okay. So the actual programming, remember this slide. Always, if you're asked to do a interfacing a microcontroller with ADC, get to know the address. So we have done it for GPIO. We have done it for PWM. Now, finally, we're going to do this for the ADC. Okay. So in this address, know what are these registers inside. Okay. And then you go to the specific chapter and find out what they do, right? And then you do the set clear. So I didn't need to emphasize again. You need to know how to set and clear bits for your target register without affecting the rest of the bits. Okay. And then now you write the assembly code for that. Okay. So there are some things that you need to know. Also additional. So you need to turn on the ADC power control, and then you need to define the clock. Same as PWM. Very similar to PWM. Okay, but more elaborate. Okay, so like what I said, step 1, find the address. So ADC address is 4003,400 in hex. Okay, 4003, 4000, right? You know the address, and you will be asked to read this special toggle switch. Actually has is a resistor that can give you the resistance level in the Y and X axis. Okay, and then you're supposed to control your ring of red LEDs. So you're supposed to read the inputs for the Y axis and the X axis, and then you write your assembly code to control the LEDs based on your X and Y inputs. Okay, and remember, for your LED is inverse logic. Okay, because of the PNP transistor. And these are the ports that you will need to take care of for your ADC. So more specifically, one of the ADC input is port 0 pin 23. Okay, for the Y axis, the X axis is port 0 pin 24. Okay, so these are the 2 analog inputs that will go to your ADC. You need to set the registers and then to actually connect these inputs to the ADC, right? Okay, so these are the steps, but I prefer to go through the schematic diagram. For me, it's easier to see. For SIM students, you have to get used to looking at this kind of diagrams. Okay, you can actually read this one, but when you start explaining to others, this is actually, to me, makes more sense, right? So you have your GPIO pin. You will need to control you need to connect your GPIO pin to the ADC. So you will need to set the pin select register, right? And this time, last time you used to do only 1 GPIO, right? Now you need to do 2 GPIO. So there will be 4 bits that you need to set. Okay. Then you also need to, because there's only one ADC, right? You need to turn on the ADC. So the address is pincon bit number 12. Okay, so I go from top to bottom. Okay, because ADC needs to be clocked. Okay, because it needs to sample periodically, right? So you need to set the clock. So you need to do clock select. And you can also disable the pull up and pull down. Okay. I will also explain to you why you need to in this particular case, why you need to disable the pull up and pull down. In your switch, this toggle switch, right? It's actually it's like a variable resistor in your, let's say for example, let's take the y-axis. It's actually a variable. When you push the switch, it's actually a variable resistor. Okay. Now imagine in a chip, you actually have either a pull up and pull down resistor. Okay, let's say pull down resistor. This internal resistor will actually parallel with your toggle switch, and you will affect your reading. So die you have to disable them. Otherwise, you will affect your switch reading. Okay, take note of that. This is lecture 1, parallel resistors. Okay, so need to enable the ADC in this case. Maybe I make a typo mistake here. There should be another resistor here. Okay, and then the outputs of the ADC for each channel, corresponding channel, like for example here, is given by this address or this name. This is port 23. Sorry, pin 23, port 0 pin 23. This guy is port 0 pin 24, and the outputs will be direct. After conversion, it will be stored in these registers, the physical hardware registers. Okay. So to read this register, right, you must do the LDR. You keep reading these registers to then you can decide what logic you want to apply to drive the LEDs. So this one is an example. Okay. So for that register that I mentioned just now, this one, how do you read this register, right? So this register is 32 bits, but your ADC is only 12 bits. So there are actually extra space inside the register. So what does this register, let's say for 80 DR0, right? So this register, 12 bits of it, right, will be the actual converted result. And then there's a done signal. Remember, you convert, you call the ADC to convert, and when it's done, it's an indicator. So there's a done indicator in that bit number 31. Okay, let me see the next slide. Okay, yeah, here. Okay, so this register that you'll be always reading for your logic, right? You will need to have the, oh sorry, this is the start conversion. So you need to write to a register. Example code here. This is my code. You need to write to a register 24 for AD0CR. When you write to it, when you set to it, the ADC will start to convert. So you go do the divide 12 times, all right, for the SAR ADC. And then when it's done, you will toggle a signal called done, and your code has to keep reading this bit without affecting the rest of the bits, right? So the moment this bit 31 is a 1, you can then write your assembly code to go and read bit 4 to 15 to read the converted result. Okay, clear about that? So this is the sequence. Now, and then after that, your code will need to, after reading, right, your code may want to go and trigger another ADC read again. Means you need to set this again, and the whole cycle continues. So you have to keep looping. You have to keep looping. You read, you call the ADC to convert ready. You keep waiting for the signal, done signal, and then you read, do your logic, do your LED assignment, then you loop back again and keep reading. So this is a continuous loop. Okay, clear about that? Any questions so far? Okay, this is what you will experience in the lab. Okay. So for the lab, the ADC is 12 bits, right? But because of your register will have some special values, so you may want to actually segment a range of values. You may want to divide out the range of values in your register. that will say, okay, if my ADC reading is within the lower range, I may want to light up LED 0, and so on, right? So different range of values, you will light up different values, different LEDs, okay? One of the tip to share with you is, okay, if you have a 12-bit ADC, so you have the MSB. So this is bit 12. Sorry, this is bit 11. So you go on and so forth, and then you have bit 0. So you may want to focus your code on the higher bits, because the higher bits gives you the higher reading, right? The lower bits may not have higher impact on your code, because 1 bit change in the LSB may not mean a huge change in your toggle. I will say, I put it this way: a big change in your toggle switch, right, will usually trigger a bigger change here in the higher order bits. The lower order bits may be just noise, right? Or you just very gently touch. These guys may not even change at all. So the significance of the higher order bits is something that you may want to focus on. You may want to mask out the lower order bits. Let's say you can do the higher order 4 bits, right? So bit 11, 10, 9, and 8. Because this one gives you the higher signal reading. Okay, and then you will have to come up with the algorithm yourself in assembly code on where to which LED to light up depending on the XY reading. So that's why I say this lab is actually the most difficult lab for the individual effort. Okay, for individual effort, lab 7 is the most difficult lab because you have to work out your own logic besides reading in the ADC. Okay, and for this lab, I want each of you to explain to me your code, or the TA. They can only sign when they understand he or me, he or she or me understand your code. Then we will sign off. And if your code doesn't make sense but still work, we will deduct mark also. So take note of that. This lab is very important. Okay. Basically, almost the end. Any questions from any of you? So first half of the lecture today is more for you to do shopping next time, right? Second half is more for the lab. Okay, so don't be too stressed about it. But the lab you must do. You must be able to know how to do yourself. Very important. Okay. If not, I release the class, and if you have questions, you can come forward. For the group A students, come back at 4 o'clock if you have not started your lab. Okay, a 3 hour. If you have not started your lab now, you may end up 5 hours. Okay, so please take note. I see the group B students tomorrow then. For your group A students, remember to mark your attendance before 6:30. Okay, for those also still in the lecture, mark your attendance before 6:30.